Nemi, thank you for joining us today. This is the Smart Manufacturing Tech Topic Series. This is our third session, and we're very pleased today to have Eyal Weiss from Cybord here today to talk about their technology. My apologies if I have mangled your name. My sincerest apologies. I've only met him over email until this morning, so I'm doing the best I can. Thanks so much, everybody, for joining us today. Just a reminder, everybody is on mute, and that if you do have questions, I would ask you to please use the chat window. I will gather those and ask those for you. If time permits and the lines aren't too noisy, I will try to unmute people and let you ask your questions directly as well. Just a reminder, this session is recorded and we will have the presentation available, and we'll send out a note to everybody that registered so that you can have access to this after the call. I have two slides, this one and this one, just to remind everybody. The point of this series is to have experts that come in and bring in various topics that are interesting to the smart manufacturing area. We are still working on adding additional speakers in the future, and I don't have any set up yet. Unfortunately, everybody's just come out of their vacation season, so I'm working to get some folks set up here for the fall and the winter and into next year. And as soon as I have those, I will let everybody know. And I would just, again, reiterate, please use the chats to ask your questions. And if you have any particular stories around smart manufacturing that you're doing and willing to share those, please add those into the chat. But otherwise, I am going to stop sharing and turn it over to Eyal. So Eyal, thank you.
Okay, here we go. Okay, can you see my screen?
Yes, sir. Looks great. Thank you.
Okay, so thanks for inviting me here. It's a great honor to be here. And maybe next time it's going to be actually seeing people in real life, but this is the best we can do now. So first I'll introduce myself and say a little bit about how I came to this business. Because I'm going to talk about something completely different, something new and interesting, and I hope that you will find, you will share my enthusiasm about this subject. My background is I have a PhD in electronics engineering, plasma physics, mechanical engineering, a lot of years, a lot of experience in the industry. I came to this subject after I was developing a new technology for 12, 15 years. From invention of a new technology, prototyping, deployment in the field, first tries, and so on. And then after a few months in the field, we started having failures. And now this is like a lifetime project, 15 years of project, a team of 25 specialists. And the system started failing one part after the other. And when we tried to find out what caused these failures, we found out that eventually they were caused by faulty components. And these faulty components were not part of the design, they came in production. And when we went to ask how come nobody checked the components before you use them, and so this is when we found out that there's no such thing as just checking the components. The entire industry is built on trust. Just buy components from your best source, and there's no checking, no validation, no verification. And this says a lot. So after the project eventually succeeded, this is what I shifted to do to solve this issue. Now, what we're saying is basically to produce your product using AI verified components and do your traceability based on evidence. Trust only what you see. If you look at all the components, your quality will be dramatically better. Especially today when there's a big disruption in the supply chain, the crisis, although it's getting a little bit better, but this significant shortage in components is causing a lot of issues, a lot of room for counterfeit components and low quality components and recycled components and so on. So all these issues today are even more emphasized, but good quality components is always needed. And what we're saying is that knowing your components themselves is the key to deliver high quality in products, because 8 out of 10 times failure in the component in electronics, if it comes from the hardware, it's actually coming from the component itself, not the process, not the design, but actually the component. For example, if there's corrosion on the soldering leads, it will cause issues. This is what happened to my project, for example. Or if the component is defective or a counterfeit, this will serve to be one of the most dominant issues in failures in electronics. And nobody today is looking at the components. The entire industry is built on documentation and trust and buying from a trusted source, assuming that everything is good. But the statistics is that about between 0.5% to 2% of the electronics in the industry are either fraudulent, there is counterfeit, or defective with defects on it, like corrosions, crack, and body defects, and so on. So what we're saying is that if you could have looked at all the components before you're using them, just to inspect them, and use only the good ones, you can imagine what a boost it will be to the quality of the products, the reliability, the costs of reworking and recalls and so on. But today, nobody's looking at the components. There's a lot of work being done and a lot of technology to monitor the process, the placement, the flow of the material, the handling. There's a lot of technology there, but nobody's looking at the actual component, and the components are the most expensive and they're the most dominant cause of failure. Now, when I'm talking about bad components or unsafe components, there may be, we can separate it to three groups, basically. So one is fraudulent components. Someone is trying to make money out of selling you bad material or not as good material, fraud or counterfeit. There could be recycled component that were pulled down from old boards. There could be fakes. This was supposed to be one, but it's actually another. They could be with forged age. Imagine that you have a reel that is 10 years old. You're not supposed to use it, but someone just changes the label and sells it to you as new. It could be a cloned computer component or leftovers from production, all kind of things like this, which all fall into the fraud category. There could be quality issues also. Defects, could be damaged, could be oxidized leads. This could be either statistical, like you have a ratio of the components have this quality issues like defects or oxidized leads. Actually, we did very, very big research. We are in our database, we have over 2.5 billion components that we already inspected, and we found out that the real numbers of defective components during the placement was about 100 ppm, and that's a lot. So about 100 ppm of components statistically are damaged, and components with oxidized lead, the number is much higher, is about 500 ppm. And this will cause reliability issues. Now, so this is the quality section. The other part is just bad information. You think you have one material, one manufacturer, one lot code, one date code, and so on, but you actually have something different. This could be either from because you had to buy the components in the free market, so it's a little bit, you're not sure about the source or where it came from, or the information is deleted, or just random errors or bugs in the process, because it's a very complicated process and it all depends on who enters the data and so on. So there can be just errors. So you could be you think you're using one material, but you're actually using something else. Now, today traceability systems are incomplete. It's either because the data source is partial, you get information from papers coming with the boxes or from the labels on the leads that someone is manually entering into the system or using a barcode scanner, one after the other, doing this for many reels one after the other, so it's prone to human error, and the details is very low because you only collect some of the information. And the most important, that there's no visual verification. Nobody really look at what is being entered, and because there's no really verification. So if you made an error, nobody will notice anyway, unless something happens. So deviations and errors are not tracked and not verified and checked. So we're going to talk a little bit of how we solve these challenges, but I just want to say as a heads up that this new traceability capability or verification capability is already a part of the component level traceability standard for the IPC 7082. So I'm going to talk about how we solve this issue, and how we solve it is by looking at our components wherever we can get evidence on the components themselves. So we can look at the reels, for example, in the incoming inspection, where you get the reels into the storage, and not just type in the fields, but we can use something more advanced using AI NLP algorithm to automatically extract all the information from all different types of reels. So there's no human in the loop, there's no error, it's extremely fast, and it's much more detailed. Then during the production, in the SMT pick and place machine, you assume that the information you get is correct, which it normally is. But what we can do is we can tap into the vision system of the SMT pick and place machines to get the images of every component that is placed on every board. And we can use that to verify that the right materials are being used and it's suitable and qualified. And the last step, we can get the images of from the AOI machines. And at the end of the line, when we look at the board from the top side, we don't care about the quality of the placement. This is what the AOI machine is doing. But what we're doing is looking at the components themselves and verify that they are what you're supposed to be, and the quality of the component is good. So what we're saying is, don't trust the paperwork. Use your components based on evidence. And I'm going to show you how we get this evidence. So what technology are we doing that? So I was talking first about identifying a label. So let's see about this. So every label is different because there are many different manufacturers and production sites. So the labels are very different. So what we did is we built an AI algorithm that is based on NLP that can understand the meaning of labels. You all probably know about NLP about when you read an article or a book and you know about the advances in AI technology in this field. What we did was we used this same technology, but adapted it specifically to be able to read the information from labels. So we can understand that one field is for the part number, one field is from the date code, quantity, and so on. And we can generalize it for all different types of components. So all this information is collected completely automatic with no man in the loop. So you get much more data and much more efficiently. So that's the real incoming inspection. We can identify the part type. Remember that we are getting the images from the pick and place machine. The pick and place machine is picking up a component, looking at it from the bottom side, taking a picture. The picture is being taken like this to do accurate alignment. Now we're using this picture in order to verify that this is a good component. So we first identify the part. So is it a capacitor or is it a resistor? Okay, so we identify what's the package case. Is it SOT23 or SOT323 or whatever? And then we're looking for homogeneity issue. Let's show an example. See, I will show mostly examples in passive components, but this is true for all the components because when we get information from the pick and place vision system, we get information about all the components that are being placed by the SMT machine. So we can look at this example. These two, where they are both capacitors, and they look almost the same, but they're not exactly the same. And these two components types were in the same reel. So this specific reel had homogeneity issues. There were two different populations within the same reel. And you can see it also in the distribution of the dimensions here in the bottom side. You can see that the components width, you have two distinct groups. You see what here, one is a 1.15 millimeter and the other one is 1.29 millimeter. So you can see that they were in the same group, there were two different groups. So this could be good, but this could also be bad, depending on the application. The most powerful tool is to identify the manufacturer. To identify manufacturer could be either to make sure that you're using what you were supposed to, or to avoid counterfeit. Because if you wanted to use Taya component, but instead you got Yagel, which is very good manufacturer by himself, but your AVL says Taya then you're using the wrong component. Now, how do I identify the component? Now you can see that they look almost the same, but not exactly the same. By your eye, you can very easily tell the difference between them. So what we did is to train an AI model based on 2.5 billion components that we have in the database to be able to identify the manufacturer based on the image. Now, because we have like 20 million components made by Samsung already in the database, probably much more, then of course I know how a Samsung component looks like. So this is what the algorithm is doing. Another interesting thing that we can do is to look at the soldering leads and try to assess the condition of the soldering leads. Are they corroded? How far along are they in their aging process? And you can do that because as the component grows old, the thickness of the corrosion layer is getting thicker and thicker and thicker, and it causes the surface to be rougher. And this roughener reflects light differently. And you can see that as the components age, the surface becomes from smooth to rough, and we can correlate it in our algorithm and estimate the age. And in addition, we can say that a component from one level of corrosion is not safe to be used because you may have reliability issues later on. So that's another thing you can do based on the images that you get. You can, of course, look for defects. These are just a few examples of defects like cracks, voids, contaminations, peel-offs, and so on. Nobody will want to use this kind of component, but these are statistics. Everybody uses them anyway, and there's no way of telling that you use this kind of component because the images that you see now are from the bottom side, which nobody sees because after you place the component on the board, you can only see it from the top side. So if you would look from the top side, you wouldn't see any issue. But these issues are from the bottom side. So you can see issues that nobody can if you're using the images from the SMT machines. There's also one interesting thing you can do is about looking for evidence of tampering. If someone burned software onto this component, he had to interface it. So he has to touch it with some kind of socket. Now this leaves marks, and these marks can be detected, as you can see. So the algorithm can also tell if this component was reprogrammed. So we know about the original one and if it was reprogrammed, and then you can alert it could be a cyber attack. And the last interesting thing to see is now when you're looking at the components from the top side, if you're looking at components from the top side, there's marking on them. But you really have to go into the datasheet for every individual component to understand what everything means. Like this part is the part number, this one is the manufacturer, country code, this one is the date code, and this is the lot code. So what we did is we used the same family of algorithm, the same as the NLP concept, to understand what the marking on every component means. So by having a picture from the top side, we don't just do OCR, we don't just detect what is the characters. We are detecting the meaning of the characters, So we can say based on the image that this one is made by this manufacturer, date code, load code, and so on. And we can use it to later on do traceability based on evidence on what you see that you actually placed. And also to do verification of traceability, because if you thought you were using date code 1.5, but you actually got 1.3, then you will be able to see it. All right, so that's the technology that we use to be able to say if this component, to say a lot of things about this component. Is it safe to use? We can classify it to different groups and so on. So every component is being analyzed for doing all these tests. I want to show you a little bit about how this works in real life. So I'm going to play a short video. Let me know if you don't hear anything, just let me know so we can fix it.
There's no audio yet. Not sure if there
There's
should
no
be.
audio? Okay.
Not yet.
There was supposed to be audio already.
Let me see if there's anything I need to do in my team's end about this. Sometimes it could be my. Let's see.
Okay, I think I got it. Oh,
You think?
you have to allow me to do the share of the sound.
Okay. Question is, how do I do that? Do you know? It's not something I do too often.
Not share sound. Go to your device only setting and select. Okay, just a second.
Yeah.
Okay, I got it.
Okay.
Yeah. Okay, now it should work.
Give it a try. Sorry about that. I didn't know we were going to do video sharing.
It's on my side.
Okay.
Is it okay now?
We're only seeing your camera. You need to share your screen. We lost your screen share.
Now you got it?
Got the screen share.
Right.
And now we got sound. Awesome.
8 out of 10 times, failure is the component fault, not the production fault. Traceability systems help reduce the recall. The problem is that traceability is incomplete. Partial data, manual entry, human error, low details. In addition, there is no visual verification of the data, and errors and deviations are not always tracked. Let's have a look at how advanced AI can take this to a new level. The starting point is a faulty board. Enter the failure data by board or by component. Find all involved boards. Select the suspect component from the list. You can also use the component's markings as identification. Here is a list of the entire involved boards. That's a big loss. Let's see how forensic AI traceability can minimize it. Run AI forensic filtering. This saves a lot of unnecessary recalls. Reduce the recall. Return faulty boards by evidence. Let's see how it plays in production. Labels are very different. Cybord uses AI for decoding the context. A unique ID for every reel is created. All logistical evidence is extracted. The reel's data is used throughout the process. The reels are prepared for the placement process. This setup is cross-checked with the reel's evidence. During placement, the image of each component is taken. We know from what reel it came to what board it was mounted, and the location on the board. Every component image is analyzed, verifying the reel content. The final station is the Automatic Optical Inspection, AOI. All the components' top markings are captured and decoded. AI content identification, NLP robust context extraction. The unique ID for every reel is cross-checked. All logistical evidence is put to use. All data is integrated. It is based on evidence, very detailed, surgical precision, ultimate control on the components, which makes it a truly reliable product.
All right, so that worked. Let me go back to presentation mode. Where are you? All right. So again, we can get during smart registration, we can get all the information from the labels. During the SMT pick and place process, we can you can use the images that the system already produces by itself. There's no need to add any hardware. This is a completely software solution. And what we're doing, we already have, we're working with Fuji, ASM, and Universal, and we have an API that they developed especially for us to be able to get the images directly from the machine. And using those images that are placed of the components right before they are placed on the board, we can get the images and we can tell each component from which read it came, to what board it went, and the place on the board. And we do that for every component that is being analyzed. And we do all these, the 8 tests that I showed before, for every individual component. So this is like the highest level of traceability possible, because you authenticate the components, you identify the manufacturer, you look for defect issues, and you read the top marking to understand the information like the lot code, date code, part number, and so on. So this gives you a very, very detailed and high level of information about what you're using. And if you have bad components, you can just remove them or remove the entire reel from the system. The idea is, because you have images from both the top side and the bottom side, so every image, every component placed, we see how it looks from the bottom side and the top side. You can see in this example here that there's corrosion evidence on the bottom side. Nobody will see it in the AUI, of course, but so you have the top view, and from the top view, you can make sure that using the right material, marking, authenticity, and homogeneity. And from the bottom view, you can check the authenticity, defects, corrosion, and homogeneity also. So you have images and information from top and bottom for every component. And then you can, based on that, you can get a board report or certification that every board with every components were tested before it was used. And now, suppose you're producing offshore and you're not sure that what material they're using for your system. So this way you can make sure that you were supposed to use a Murata component that you actually got a Murata. Now, a very, very powerful tool that is now getting into the IPC standard also is to be able to verify your traceability information. Currently, even if you're using level 3 or level 4 traceability, which is very good, it means that you can trace back every component to every board, and you can tell what lot code or date codes of a specific components were placed on what board. And this is very good. But it's wrong, because nobody verifies that this is true. So you assume that there were no errors in the process, there's no mistakes, everything is completely smooth, but you don't actually verify it. So because we're getting the images from the top side of the component, and when you're getting all the logistical information, we can compare the traceability reports to what we actually see. And we find some very disturbing stuff. From level 4 traceability, they were supposed to be perfect. We found out that there's many errors, like items that don't have data, or items that the data is wrong. For example, someone scanned some other code to the lot code, and it's not a really lot code, or the same component has different lot codes it was belonging to, and many errors in traceability that can cause you an issue that when you have to do a recall, you actually can't, because the data is not true. And there's no verification for this today. So this tool can be a very, very powerful verification tool. Again, we get the images from the top side, we decode what it means. You can see in this example, so this is a component, Marconics. And the marking here is 2215, read from the component. And this is what actually is from the information. So this is correct. So it verified the marking date code. You got the load code. It's also verified against what we know earlier about load code and so on. And we also know that this is a Marconics and we know the part number based on the top image. So this is also a very, very powerful tool. So this is the first solution to comply with IPC 7082A for class B and C, which is component level traceability and the new traceability verification capability that's just introduced to you. And again, this is based on software only. You don't have to install any hardware into the system. I'm not sure that I have enough time to talk about the difference between the traceability levels. You're probably familiar with it at least to a level, but the current traceability level, let's say level 3 and 4, means that you can identify you have a unique package ID on the reel, you have a unique serial number on every board, and you also know which component went to which location on the board, the refless. And this is currently the highest level of traceability. Now, this level of traceability is called level A, or individual component traceability. It gives you not just the level of give you the information about which reel it came from, but the individual component that actually went on the board. So let's say, for example, that you had an issue with a component that were failing in the field. Up till today, even if you had level 4 traceability, you still have to return the entire packaging unit ID, the entire reel. So it could be 5,000, 10,000 components. But suppose the failure came from a capacitor that had a specific visual feature that we can separate. Let's say it was, for example, with corroded leads. So we can tell you, you don't have to recall the entire reel. I will tell you which is the 100 components that have this issue. So this way you can only recall the 100. So this has become a known issue. Instead of doing a recall of 5,000 components, you only recall 100. And we have few examples at our customers just lately that a very, very big recall was avoided because of this. We found the root cause visually, found similar components because we have all the components in the database. And then we were able to reduce the recall dramatically. Well, these are the standards. So just do a quick recap, so will be hopefully time for questions. The idea is to know the components based on what you see, to focus on the components, because the components are responsible to almost all the failure of hardware in the electronics. It's very important to take good care of the components. Nobody's doing this today. And what we believe is that the current method of using only documents as a way to say that the material is good or bad is working, but it has a very big cost to it. Recalls, reworks, failures in the field, reliability issues. Sometimes they can be just statistical, like you have a 1.5 recall percent. Sometimes they can be catastrophic, like the project I told you about was a $1 billion project, which was almost canceled because of a 3-cent capacitor. So it could be devastating or statistic. So minimize the recall cost, watch and analyze all the components that you use, make smart decisions based on evidence. Now, know that because you have so much information, you can do analysis, statistics, what's being used, how much it was used, who is the better manufacturer, what is the ratio of defects we have in this manufacturer, and what is the homogeneity issues we had with the other. So you have a lot of information that you can use to make smart purchases and smart utilization of material. There's no human in the loop. It's completely software solution, no hardware needed. And it allows you to do surgical traceability. So you can identify individual component going in individual board. And when you do have to recall, you can recall only the ones that you see that have the problem and make it a non-issue. So thank you very much for your listening. I hope you're there because I don't see anybody. But
We're here.
I'm looking forward to hearing your questions.
Excellent. Thank you, Eyal. If anybody does have questions, I would say please use the raised hand function or put it into the chat window. I do see a couple of questions in the chat, so I'll ask those, I guess, in the order that I got them. Amba asked about, is there any data on the effect of faulty or compromised PCB material on the quality of PCBA?
Well, this is very interesting because this is something that we're currently working on to get information, because we have an algorithm that can process if there's corrosion on soldering leads. The same algorithm works also for PCB pads. So we are also looking to qualify boards, again, using the same vision system that is already in place. So we can get images from the SPI machine, for example, or even from the deck, and to try to get and see and evaluate if there's a degradation in the quality of the pads on the PCB. Of course, if there's degradation in the quality of the pads, it will affect the bond. Needless to say, the same way exactly as if there's the corrosion issues on the component, it will have a devastating effect on the reliability of the board. Now, bear in mind that this is not a solderability issue, because today's solderability with the advanced paste and fluxes will get it together. I mean, it will be together and will pass the tests and during the assembly, but it will later on fail in the field statistically because the bond is contaminated. So thanks for the answer.
He said that clarified that. It's great. We had a question on customers. Is that do you already have they say OEM customers, like probably any customers, but that are using this platform technology? And then I sort of have a follow up, and is like, you mentioned this is a SaaS solution. How is that being implemented, and does it matter how old equipment is and things like that for the solution? So those are sort of one question, and then me following up a little bit more.
All right. So yes, it's a product. It's already working for I think about a year and a half now. We're deployed in about 55 production lines.
Okay.
I think in a major manufacturers. So this is, and we're accumulating data. We are a big data and AI algorithm. So the more data we collect, the more accurate we are. The accuracy as we are is about 99.85%, which is very good. And yes, this is used for real customers, for real products, and it's very, very powerful tool. About the hardware. Currently, we are integrating with all the AOI machines that we know of, at least. That is Koyang, VI Technology, Vitrox, Holy, Omron, PRI. And from the pick and place machine, we are currently working with ASM, Fuji, and Universal. But basically, we can expand to others as well. Now, the only thing that we must have in the SMT pick and place machine is a camera. So it has to have a camera for doing the actual accurate alignment. So, for example, old models by Juki are not going to work because they're using laser alignment. But that's almost, and I think also KNS old models using only laser alignment. But beside that, all the components, all the machines with vision system will be supported. If it's very old, then there could be compatibility issues. But with the machines that we work now are about up to about 15 years old. So if you're younger than that, it should be okay.
That's pretty good from my understanding. Okay. I have another question, but I want to open it up to the audience. So first of all, is there anybody else that has questions that's here today? Please use the raised hand function or type in the chat window. Give them a second. If I don't see anybody, I have a question as well. Okay, so my question, and because your solution is different, maybe it isn't as applicable. How, I guess, how are you training the AI? I know you in the beginning of the presentation you mentioned like you have reels of Samsungs and TIs and other things, and it's taking pictures of all of those, and it can compare to those. It's like, how do you start that? I guess, how did you start that process? How do you continuously improve that process? And like you mentioned, it can identify corrosion. How is it doing that? Is it comparing it to a image database, or what can you elaborate on in there? And maybe it's my lack of understanding of the details, which you're welcome to tell me that.
So I don't know, an average production line or high volume production line can do about 1 million components a day, maybe less, maybe more, depending how high volume it is. So imagine that we have 1 million components a day that we can use for training. Now, when we do the training, of course, the data completely remains anonymized. So when we process it, there's no way of knowing where the data came from or who's the customer. So everything is completely anonymized. What we do get is what's the logistical information. So who's the manufacturer of the component, lot codes and date codes and so on. So we get this information, and we first have to make sure that we are using that the information that was given to us by the setup system is correct. And this is the tricky part. So we have a lot of tests that we do to qualify a component and reel to be trained based on it. It includes using a lot of data from different sources and doing a multi-layers AI algorithm to make sure that this is not a contaminated reel. Then we can have, we basically have a lot of labeled data, and we can use it to improve the algorithm, the classification algorithm more and more. Whenever we encounter a material that we didn't know before, we can add it. After we carefully check it, we can add it to the training set, and we can then learn how it works. When we started, the database wasn't as big. So there was a period of learning for every site we deployed because we learned new material. So we took the first 2 weeks to only collect data and screen it. And then we selected the one that we can use, and then we updated the models. So this is how we gradually go. Now we are in the stage that there's almost no difference because the database is quite big.
Okay.
Oh, corrosion. Corrosion is very important.
I just used that as an example. I mean, and any of the things that you were able to detect, corrosion was one you had mentioned.
The corrosion is more difficult because people ask us, how can you say at what level is the corrosion problematic? Well, some may say, okay, I don't want any corrosion, and some will say, okay, corrosion is a fact of life, but we live with it by also. So we have to find the right limit, and that's very important. And what we do is we are with our partners, we are labeling components that we think that are problematic, and then we track them on during their ICT testing and so on to find out if our predictions were accurate. And this is how we balance the level of the threshold where we disqualify a component and when we let it pass, although we find components leads on. And we're also a part of many failure analysis, because suppose you have a failure in your product. Now you have a tool that you can see what components you placed, not what type of component, but you can see the individual component that caused the problem. So you can see that, okay, I had a failure in the ICT. Let's look at how the component looked like during the placement. So you have a picture from the bottom side, from the top side, and you have the test results for all the testing that we did, the defects, homogeneity, corrosion, authenticity, and so on. So you can find if this was the cause of your problem, because it could be this and it could be something else. So because of that, we're a part of many investigations into failures. And we used it also to help us calibrate the model.
Excellent. Excellent. We've got another 5 to 10 minutes for folks that, if you want it to, are there questions? And Eyal, if there's anything else that you want to emphasize or clarify, please feel free.
No, I just want to say that this is a really a different way of thinking about production, because today production is going into looking into the process, the stability of the process, the analytics of the process, the setting of the machine, all this, getting information from the machine. This is something different. We're getting a new information that is not out there. We're getting information directly from the images of the component, and we can do smart decisions based on it. And that's a real difference. This is a real chance to make a real difference on the quality of the products, because nobody knows why 1.5% of the products fail or come back. Nobody knows. Just live with that. And it's not necessarily, you can go back to the basic level of reliability that we're supposed to have, which is about 0.1 to 0.2% of returning a year. And nobody knows why is this gap. And with this method, you can make sure that you're using only good components, and you can track it during the lifetime. So you'll have evidence that you're using only good components, and you make sure that you're using the right ones. So I think this is the message that I'm trying to say, that you have to look at your components.
Okay. We got one question in while you were talking there, and from Jason. Any plans or possibilities to include additional verification sources such as electrical testing, etc.?
Well, the algorithm, we're currently focusing on using images to do the analysis, using the deep networks in AI. But basically, conceptually, you have to have some kind of fingerprint that you can use as a comparison method. In the beginning of the way, we also used IR spectroscopy to have another measurement of the components, and to make sure that the reflected light this was used as the fingerprinting or the measuring tool. And it worked, but we found out that the image analysis is much more powerful, and it made the IR spectra or the light spectroscopy redundant. I hope it answers the questions.
Looks like Amba came by with another, I guess, comment, saying that sometimes the component sourcing is done by, he says, new staff. So I guess, like new hires and things, that could also lead initially to trouble, I guess, associated with
the
staff
problem
training.
Is it's sensitive to human error, to error in handling, to just mistakes that being done. Assuming that everything is perfect from the production of the component till the placement on the board, on the reflow, is naive. It's not. Because we're seeing so many components that we are processing every day, we're processing about 250 million components a month now. So it just, we don't see it. We see many issues and many errors and many mistakes, and we're working with the best of the manufacturers. So assuming everything is correct along the way is, of course, naive. And you're right in what you're saying. Sometimes it's a new operator, sometimes it's disturbed, sometimes it's just human.
Yeah, haven't had their coffee yet, or had too much.
Yeah.
Understood. Excellent. I don't see any further questions, so I would ask if folks do have questions, please email them to me. I'm marques@inemi.org, and I will get them to the Cybord team and get you some answers back. But I want to thank Eyal and his team for putting this together, and I know we had some challenges earlier in the summer to make it happen, so I'm glad they were able to stick with it and come back here at a later time and present to us. I think it went well. It gave us more time to actually get some more folks engaged as well, I think. So I appreciate all your time, and I'll turn it back to Eyal if he has any last words.
No, just feel free to reach out, and any question or clarification, we'll be happy to elaborate, demonstrate, and so on.
Awesome. Well, thank you again very much. Thanks everybody for your attention. And as I said at the beginning, we will send out a link to the recording and a copy of the presentation to you probably here in the next week or so. So that you can have, and even those that are not on the call will also get a copy of it so that they can see what they missed. And I will follow up once we get some more Tech Topic series speakers lined up. So thanks again and have a great day. Appreciate your
Thank you,
time.
guys.